In this poster presentation, I intend to introduce to you the concept of bacterial growth, discuss our proposed method of reducing this growth, and other future patterns and fabrication methods we hope to explore. I want to start off this presentation by giving you a little bit of context for why this research is important. Bacterial growth occurs when bacteria adhere to a surface and begin to grow into a colony that rapidly spreads. These surfaces tend to be smooth, which provides optimal growing conditions for the bacteria. Surgical implants such as hip implants, catheters, and pacemakers are a perfect breeding ground for bacteria, which can lead to serious and sometimes life-threatening infections after surgery. Bacteria on these implants form what is called a biofilm, a colony of bacteria protected by an extracellular matrix. These biofilms are nearly impossible to clean and sometimes require the entire implant be replaced to mitigate risk to the patient. Many methods have been proposed to reduce or inhibit the formation of these biofilms. Research in this field is divided between two ideologies to reduce bacterial growth: chemical inhibition and topological inhibition. Methods in chemical inhibition rely on the idea of releasing bactericidal chemicals, such as gold and silver ions, from the surface over long periods of time to prevent the settlement and formation of a biofilm. Topological inhibition methods rely on using surface topography to damage bacterial cell membranes or otherwise disrupt growth of a biofilm. Both cicada wings and gecko skin, pictured here, are covered in a lattice of nanoscopic cones which have been observed to reduce both wettability of the surface and to tear cell membranes of invading bacteria. The problem with replicating these surfaces is the challenge of creating patterns on the scale of nanometers or even smaller. These materials can be quite costly to produce, which makes them less than ideal for mass use in the medical field. Our research focused on creating surfaces with larger scale patterns that can be mass-produced in many labs without the need for additional costly equipment. Our method uses a process called photolithography to transfer a two-dimensional pattern into a three-dimensional pattern on our surface. A clean silicon wafer, acting as our surface, is first coated in a 2-micron deep layer of positive photoresist, a liquid polymer that breaks down in the presence of UV light. Our pattern, printed on a clear transparency, is then placed on top of the sample and exposed to a UV light. Photoresist not shielded by the pattern is then washed away in a developer solution, leaving behind our pattern is a 2-micron high raised surface on the sample. We call this sample our master copy. We then needed a method to create copies of this master to ensure our pattern had transferred correctly. To do this, the sample is first coated in trichlorosilane, or TCS, an anti-adhesive that prevents our sample sticking during the following steps. Polydimethylsiloxane, or PDMS, a liquid elastomer, is then poured onto the master and baked in order to solidify into a negative mold of our sample. Once the negative copy is separated from the master, the process is repeated on the negative copy, first TCS treating, then PDMS coating and baking to produce a copy of the master. This copy can then be analyzed in a scanning electron microscope and the process repeated to refine our methods. Using this process, we were able to create a number of viable samples for future bacterial testing. The patterns shown here are examples of patterns that can be fabricated using our process. The squares and lines on these surfaces are each 20 micrometers wide and an approximate height of 1.7 micrometers. Features of this size have not been explored much in the literature and provide an interesting opportunity for new discovery. Future work with this research will involve culturing Staphylococcus aureus bacteria and planting it on surfaces to observe any effects on bacterial growth. Another method we hope to explore is using the naturally rough surface of black silicon to create patterns resembling the gecko skin and cicada wings mentioned earlier. Other research has found that black silicon exhibits a high bacterial kill rate and shows promise as an antibacterial surface. However, the sharp edges and fragile structure of black silicon make it inconducive for implantation in the human body, as they could do more harm than good. We theorized that by using the TCS-PDMS process mentioned in our fabrication methods, we could create a surface that would still maintain the bactericidal properties of black silicon while also being safe for human implantation thanks to softer, structurally sound PDMS tips.